Okay, so this is just going to be a quick introduction to injection molding. We can talk about 10 times as many things as we're going to talk about now, but I'm just going to give you the basics, okay? That's a transport container. It's like this big, fairly big thing. That transport container is made by a company that's just up here, actually. It's quite close to Trondheim, quite close to the airport. The lid of this container is made in a big machine, and that machine is about the size of a bus and probably a lot heavier. It's huge, right? And the reason it's huge is that when you make stuff in plastics like this, the way you make it is that you start out with plastic pellets, like little beads, and then you heat them so they melt, and then you squeeze everything into a mold, right? Using super high pressure. And because the pressure is so high, you need high pressure to get the details right. And since the pressure is so high, you need a really big and strong machine just to keep everything in place, okay? That is the production tool for that one lid, right? This is, I'm not sure if, does it say the weight on it? No, it doesn't say, but it's like several tons. It's enormous thing, right? Again, it's enormous because the pressure is really high. But all of this means that when you make stuff for injection molding, when you design for injection molding, the unit cost is low. Like making one of this takes like 1 second, right? I can make like 10,000 of these a day. But the upfront cost is really high because you need that production tool and you need that machine, right? So the bottom line here is that injection molding is great for stuff that comes out in high volumes. That's one takeaway. And the other takeaway is that when you design for injection molding, you really don't want to make mistakes. If you design something that does not work and you invest in a tool that's this big, that costs like several million kroners, like million euros for that matter, it needs to work. So you need to be dead certain that it works. Okay, same thing goes for headphones and everything else. So no pressure. So let's look at a machine that's actually doing stuff. You know these kind of things, like Lego bricks. These parts are made in a machine that looks like this. This is from Lego House in Denmark. That's actually me in my summer outfit, just looking at this great little machine doing its thing. So that's sort of what it all looks like when it's running. So what happens now is that it fills the mold, that's pretty quick, and then it needs to cool down, right? Because otherwise you cannot let the parts out when they're too warm, they will just warp and do things, right? So that's typically what it looks like when you do injection molding, right? Big machine, big tool, fairly quick, and this is a multi-cavity tool, so it makes several parts at the same time. Yeah?
Question.
Yeah?
When you look at injection molded parts, you have these small like circles with push pins.
Yeah.
Is that from the process? Like,
it's from,
because it's still
yes.
warm enough to make the imprints? Of
it's actually not imprint, like it's, there you can see the ejectors, right?
Yeah.
It's not imprints, or well, it's not because of the pushing. It's because you have little pins that push out the parts.
Yeah.
And those pins are like they're on a surface, right? But they're not perfectly aligned to that surface. If they are off by like 1/10 of a millimeter, like too far in or too far out, it's going to be visible, right? So the little round things you see is, it might be the air gap around the pins, or it might just be the offset between the pins and everything around it.
It's not a footprint?
It's not a footprint, no. It's just alignment. Maybe like in some cases it will be a footprint, but in most cases it will not. Yeah. That's actually better going slow. So, okay, so first part of the process, right? We fill the mold, right? And then you can see there are some cables here, and this is cooling, right? So you melt the plastic, so that's super warm, going into to a mold that's cool. So you extract the heat and the part solidifies. It's like making ice cubes really quick, right? And that's why you need to wait. You need to wait for the part to cool down before you open the mold. It's not the process of like getting the plastic in the mold. It's just like cooling down the part. That's the waiting part. And then, don't do that. computers are hard. Yeah, and then the mold opens like this, right? Part is here, and the part is a mold like this has two sides. It has a core, that's the center, and it has a cavity, that's the thing around it, right? And plastic has a tendency to shrink, right? When this thing cools down, it shrinks. So it tends to stick onto the core like that. So this opens, releases the cavity, and then you just need to sort of push that part out, essentially. And that's the last thing that's happening here. Like you can see it's being pushed out. Oh, there you go, they're pushed out. And then once that's happened, you just close again, and then you make a new part. Okay. If you look at the Lego bricks, see? Oh, this is just too good. Like a number of, maybe it's down here. You can see there is an inlet, like the gate where the plastic comes into the part. Like on this part is that little thing underneath, right? So typically injection molded parts, they will have traces from the injection pins, and then they will have traces from the gate, and those two are often on the opposite sides. You can do some tricks to get the gate on the side and everything. Like on headphones, it's going to be quite hard to see it. Let's see if you can see it on the Lego bricks. Yes, you can see it. That's the gate. That's where the plastic comes in, and then it's ejected from the inside. You can just pass that around. You can pass that too. Mm-hmm. So far, so good? Yeah. Then there are at least 4 things you need to know about when you make injection molded parts. And those are these things: drafts, sink marks, thicknesses, and undercut. The list, I've got a far longer list, but this is the core of it, the essence of it. The first thing you need to know about is draft. So when you make something, it needs to come out of the mold, right? You cannot do straight sides. But then again, you can on a Lego brick because the outside is straight, but there's a draft on the inside, so that kind of works anyway. So when you look at any injection molded part, most parts will have drafts, but the drafts can be really hard to spot unless you know what to look for. If you got a rough surface, I can do some sketching. You need more draft than a polished surface. You can see that Lego brick is polished on the sides. Ribs and gussets can be close to 0. Round sliders, if you have something with a round hole inside, you don't need a draft for that one round hole. Do we have anything with a round hole inside? No? Maybe this? Yeah. That hole does not need to have a draft, because in production it's made by an axle that you just pull out, and that will usually work without a draft. In other cases, if you don't have drafts in other cases, you will just you will just rub against the part as you take it out, and it's going to look ugly. But there is an exception for round axles like this. You can pass that around. Yeah. And also, when I say gussets, do you know what gussets are? Like ribs? Like when you make something that's injection molded, very often you will reinforce it with ribs on the inside. Yes, I was lucky. So you will have this kind of structure on the inside just to make it more solid, right? And if I draft that gusset, if that has like a trapezoid shape like that, the footprint or the interface towards the outer shell is going to be very big, and that's going to lead to sink marks as well. But we're going to talk about sink marks later, so let's start with the draft. So you just look at that as well, just pass it around. So let's do some sketching. So what all of this means. Share. Oh, don't do this. There we go. Yes. Okay. So let's say I want to make a box. I want to make this, right? So that means that if I do a section, if I just cut this across and look at how this thing looks, it looks like this, right? And then my production tool is going to be a core, that's the center part, and a cavity, that's the outer part. right? So this is easy to get out of the mold because of the slanted sides, right? That's the first point. That's the draft. And the draft is simply that angle that you can see here, like the deviation from the normal. And that's typically 1 to 2 degrees. Okay? So far, so good. If this wall is textured, let's say it's not polished, it has some sort of texture, like this kind of thing, right? Then that wall becomes rough, right? So it's, let's say it's a rough wall. Can we just zoom in on this? Come on, zoom in. Yes. So that wall is now rough. It has like little particles on it, like that. That's the wrong color, sorry about that. Imagine that would be black. Black, yeah. So it's a textured wall, right? And because of the nature of the texture, if that is very rough, of course, you will not have that 1 degree draft on the top here. It's going to sort of rub against the mold, right? So to counter that, you need more draft to release it, right? So if you have a very rough texture, like on the sides, you can see that there's more draft. This is actually a good example. You can see on this remote, it has texture on the sides. The drafts here are actually quite big just to get that out of the mold. So Lego brick, straight side, polished, remote, rough sides, textured, big draft. Okay? Yeah. Let's draw a gusset. If you take that drill, let's take the case of the drill. So if I just take the handle of that drill, let's see, once again, or like any part of that drill, it's the half moon like that, and then it's got little ribs. So it looks like this. That's the outer shell, and then it has little ribs in it. It has like tons of ribs, like that. That could be like one part of the drill, right? It has gussets or reinforcements to it, right? So when I say that drafts on gusset can lead to thick corners, what I mean is that if this is drafted like this, that's a huge draft, right? Maybe that's 5 degrees or 8 degrees or I don't know. Oh, my bad. That's a huge draft, right? Maybe it's 5 degrees or 10 degrees, I don't know. It's a lot. So what happens now is that this gusset becomes very thick at the base, right? And we all agreed that plastic, it shrinks as it solidifies, right? Right? When plastic solidifies, it goes from molten to solid, it shrinks. So what's going to happen here is that I got a big lump of material and it shrinks. So what it's going to do is it's going to pull on that surface and I'm going to get like that kind of a shape. And that looks ugly. That's called a sink mark. And we can have examples of sink marks. Let's see.
You have it on the chair. Very small.
Oh yeah. Oh yeah, this is great. Yeah. If you look at this in the right light, you can see there are dots up here. And those are sink marks from the towers that are... Actually, it's a bit strange that they're on there. Are you sure that's a sink mark, Jon? It's not just like the screws pulling on it? I'm not sure if that's the best example. Oh yeah, because there's a little tower. Yeah. Okay. Yeah. Yeah. So there's a screw tower. Like the screw goes into a little pipe on the back, right? And you can see if you hold it the right way, you can see that there are like you can see the sink marks, right? And also this is a good example of sink marks. Like here's a big chunk of plastic, and you can see on the top of that tower, like the top is not flush. It's like it has a little dip to it, and also on the inside, but a lot on the top. You can see it says too thick. That's a sink mark, right? And those sink marks are there because the plastic shrinks as it cools down. So that takes us to our next point, sink marks. Yeah. So typical shrinkage is 1 to 1.5% for ABS. It might not sound like a lot, but what this means in practice is that when you do injection molding tools, you always make your tool bigger than the part to compensate for that shrinkage, right? The tool needs to be about 1% bigger, because otherwise your part will be 1% too small. Makes sense, right? If your product varies in thickness, that's when you have problems with the sink marks. So it's perfectly okay to have something that has a thick wall all the way. It's perfectly okay to have a thin wall all the way. It's not okay to go from thick to thin, and it's not okay to have a thick wall touching a thin wall. So going back to my example here. So what happens here is that I got a thin wall, right? And then I got a thick wall, and where these two things touch, I will get a huge mass of material, and that's going to pull on that surface as it shrinks, right? That's a sink mark. How do I prevent this, like for the case of the drill or for the case of that stool? Like, how would I avoid this?
Smaller gussets.
Smaller gussets, yes. How small?
Small enough to not get shrinked.
Yes, there's a rule. There's a nice little rule, and I can show it to you. So if I have a surface and I have a gusset, the rule is simply if that surface is 1, then this should be not more than 2/3. That's a great little rule. So that means that the footprint of this, if this is, let's say it's 10 millimeters, this should not be more than 6.6 millimeters wide where it touches. Easy as that. If you do that, you don't have to worry that much about sink marks. Okay? Let's say we make a big gusset here that is a lot wider, right? And then just to illustrate what's happening here, I'm going to make some circles. So let's say that I can make, this is sort of my circle, I can make this all over the place of this section, right? And also the circle that I can put in here, which is just like the volume of material just in that location, they're about the same. But if I have this big gusset, that means that my volume when I do a cross section is a lot bigger. And that's going to give me the problem, right? Does that make sense? Yeah, so if you have like large masses of plastic one place, that's where you get the sink marks. 2/3 is a good rule. That's 1, that's 2/3. Okay, so going back to our drill example. So you were saying that, of course, I can reduce this gusset. That would help on the sink. What else can I do? Let's say you talk to an engineer and he says that you cannot reduce that gusset. It needs to be that thick to be strong enough. So I insist that you will have to do a ridiculously thick gusset for some reason. What else can we do? Yeah.
Can we make it hollow?
Yes, you can core it. That's a good. I didn't think of that, but that's really nice. That's a very good strategy. You can make it hollow. So yes, we can make it thinner, we can make it hollow. Is there anything else we can do? I insist that it needs to be massive. Like seriously, I'm not making it hollow today. It needs to be like that. Yeah?
You can thicken all the other walls?
Yes! Yes! If I just do this gusset is not a problem anymore, right? Why, in what cases would this not be a good solution? Yeah?
You need the wall to be smaller?
Yes. And why? What sort of drives my wall thickness?
The components inside and the design outside for your headphones, for example.
Yeah, but why don't I make headphones with like 8 millimeter walls on it?
Heavy, expensive,
Heavy and why is it expensive?
because you have more material.
Yes, but there's another reason why it's expensive too.
And it takes longer to dry.
Yes, you've had injection molding before. No? Yeah, but that's good thinking. Yeah, it takes longer. The cycle time is a lot longer as you make thicker parts, right? And that's also part of the cost. So it's material and cycle time that sort of makes up your cost. But yes, we make it thicker. That's fine. But let's say I insist, okay, I will not make it hollow, I will not make it thicker, I will not make that thinner. There is also like the option of just living with that sink mark. Seriously, it's not. The example here is from a virtual. It's an electronic cowbell, right? This is something that is used in agriculture, and it's got some huge sink marks going on, right? But it does not affect. It does not affect like the strength of the part. It looks a bit ugly, but no one really cares. This is going to be covered in mud anyway. You can just live with it. Sometimes you do not do that on flat screen televisions and the like, right? You can do it sometimes. If it's packaging, if it's something else, you might live with it. Last but not least, if you texture a surface, like if you add texture to it, like this kind of thing, that hides the sink mark. Because a polished surface is like a mirror. Like if there's any defect, it's going to be very easy to see. If it's textured and also very, very coarse texture, it's going to be really hard to see. Okay. So yeah, thickness variation, sink marks, coarse surface hides it. Polishes are difficult. It's not a deal breaker. And also avoiding sink mark comes at the cost of strength. Like going back to our gusset example. If I need to make all of my gussets and the structure inside super thin and fragile, that's also a drawback, right? So you need to find the right balance. When you do your headphones, the easiest way to determine the wall thickness is to just measure off the other headphones, like the ones we took apart. And that's also what we do like in my other job. If we make something, we don't reinvent the wheel. Like you can always optimize the design, but like if you just want to get the principles right, start out by just copying wall thicknesses from something else. Most of the times that will get you all the way. Okay. So we talked about draft and we talked about sink marks. Next up is, and we also did actually talk about thickness. Like typical electronics, 1 to 2 millimeters. If it's structural plastic, you can be a lot thicker. Reasons for going thin is that you will save material, you will save cycle time, and it's also you get lighter parts. Reason for going thick is that you get stronger parts, you hide sink marks, and also you get better quality feel. Like if you say something feels plasticky, like the interior of a Mercedes is mostly plastic, but it doesn't feel plasticky. So feeling plasticky is more about how you design stuff than actually stuff being made from plastic. All right, so just try and get a feel for what feels cheap, what feels expensive, and why that is, right? Yeah. Now it gets a bit more complicated. Do you know undercuts? Okay, I'm going to go back to my bucket. I'm going to go back to this. So I'm in the bucket business. Like this is what I had, right? If that bucket, let's say I want some sort of feature on it. I want a little hook on my bucket. So let's zoom in like that. Let's just take away that part of the tool. I want, I need something to attach to a clip. And that needs to be, I need a little step. I need a little feature that looks like this on a bucket, right? Just a little step like that. That's going to give me a problem because this is an undercut now, right? I cannot simply have the inside of the tool. If the tool just follows that, I'm not able to manufacture that. Agreed? I cannot pull this red part out of the box without damaging that little flap. That's not possible. So how do I solve that? Magic. Yes, I need some magic. Yeah.
2 parts.
What 2 parts?
The mold.
Yeah.
2 parts.
How do I do the 2 parts?
We have a split line like this.
Yeah. So I can. Hopefully, we think of the same thing here. I can split the inside of this mold. This is kind of magic. Like if I take a line going here to like that, like this, that's very thin at the top, but okay, bear with me. And then I make 2 insides, like that. Then here's the trick. So this is called it has many names, but it's often referred to as a slider. So imagine when you release this part. I'm just going to try and make an animation on a remarkable now, and that usually doesn't work that well, so bear with me. Imagine when you release this part that you take all of this, with the exception of that top triangle, and you pull down, right? You pull this down like that. And then as you pull down, since that's at an angle, you pull that inwards. So you take this triangular thing and pull that inwards like that. That looks a bit messy, but I'm going to clean it up. That's a nice little trick. That's called the slider. So now I'm left with that part is stationary. This thing follows the part out, like to a certain extent. But because that is an angled line, it just slides to the side and it releases that little flap. That's pretty clever, isn't it? And that's how you do undercuts when you're on the inside of something. My example was, this little pocket you can see here. If you zoom in, like you can see there's a little contour. You can see a little squarish thing here, right? Really hard to see, but you can see a line here, right? And that is the footprint of that slider. That does exactly that. It comes down, it follows the part out, and it goes sort of sideways out of that pocket, and then your part is free. So that's how you do sliders. And if you look at your headphones, or anything else for that matter, you will see traces of sliders everywhere. Like anything that has a clip or anything like that will have a slider. That's not a good example. I'll find some examples. Do you have some examples, Jan? Sliders? Sliders? Or do we have some parts from the teardowns? No.
The cube has sliders.
Hmm?
The cube.
Yeah, the cube has it has a different kind of slider. Yeah. That works on external geometry. You can use hydraulics and you can do things just to pull away from the part. But when you're on the inside, you need to do the little trick.
This one has a lot of.
Yeah, that also has a lot of undercuts. Yeah. There's also a different way of solving this. Let's say I need this little step. Maybe we can go to the mire board, see if we got something there. Yeah, here you go. You see this little square kind of thing here? That's probably the trace of a slider that's used to make that little clip you see on the sides there. Right? And you will see this all over, like the insides of products like this are quite ugly looking. Let's see if we can find some more. So whenever there's a clip, like any undercut feature, you will see a slider close to it. So the essence here is that it's okay to do clips, but you need to add a slider. And rule of thumb is that a small slider is like $1,000. So that if you got like four clips, that's $4,000 of sliders. But if that tool is like $20,000, it doesn't really matter. You're fine. Let's see if I got some. Oh, here we go. Here we go. Look at that. 3 little clips. And then you can see the slider next to it, right? All agree we need sliders. Very useful. Let's say I don't want to use sliders to make my clips because I don't want to spend the money on a slider. So I will just do this all over. I'm going to make my box again. So my box should look like this with that step. I don't want to use a slider, but I want that step. That step is super important for me to snap something onto it. Are there other ways I can do this?
Can you do the injection molding in 2 times? If it's still warm enough to slam another thing in or something?
No, but you still, even if you slap something in, you sort of need to pull that tool out.
Yeah, okay.
So I need, okay, I'll give a little hint. It does not have to be waterproof. Yeah.
Ice?
No. Now we're getting into very exotic processes. But
Like in water suspended injection molding?
hmm?
Like you do it in water?
No, it doesn't really help
Can
me.
you
Yeah.
sort of weld two injection molds?
Welds?
Yeah.
You could, but it's not practical because I want to make like 10,000 of these a day. So I want it to be just like super automated. Yeah.
Maybe a slot so something else can get into it.
Yes. Maybe a slot so something else can get us into it. Let's look at this. Let's draw the core and the cavity again, right? We had on the outside, we had the cavity like this. And on the inside, we had the core. But the core is giving me a lot of trouble. I'm just going to sketch it anyway. And then something is going on here. I don't know quite what. And then that's the core, right? But this is my problem area. But imagine if this outside is not visible anyhow. What if I just make a big hole? And then I take my cavity, the blue part, and I just let that sort of make up that part of the mold. And then I do the core like this. What this will now look like is I will get the snap, but underneath the snap there's going to be a square hole, right? So going back to the Miro, that means for this case, I will get this, but the cost of getting this is that I'll just get a hold straight underneath it. And that's fine, provided it's not a visible surface. On this headphone, that is a visible surface, but you can see the insides, look. You can see there's a hole here, there's a hole here, and a hole here, and those holes are probably there to make the snap surfaces that are there, because this is not a visible surface, right? And that is called a cord cut, right? So whenever you have something that doesn't need to be waterproof, it's not visible, you can just do a cord cut. You can just make a square that's the footprint of whatever snap you want and just like pull that through the wall. And then there are some rules on draft angles and everything else, but you don't have to worry about those. Just know that there's a principle called cord cut, and you will know more than most people about injection molding. Let's see if we find some other examples here. So you'll typically see this on internal parts. Oh, here you can see sliders. Not a whole lot of cord cuts, but you could imagine. You could, if this was not a visible surface, and it's not, you could save money by just making a little slot underneath here to make that clip. You don't really need that slider. That's the essence of it. Okay? Yeah. That's actually it. If you want to know more about injection molding and designing for plastic, that link actually works still. That takes you to the handbook, which I've also posted in the announcements. That goes more into detail about these things. Since we got a bit of time left, I can show you just how to do drafts when you do your CAD. Right, so here's my headphone, right? And I want to make sure that this is manufacturable. So let's work on the cup. Let's just isolate that like this. Okay, so here's the cup. I'm not really certain if this thing comes out of the mold. I don't really know what's going on here, right? But luckily there is a tool called, let's see, inspect, draft analysis. This is golden. So my problem now is that this line is not straight. My top line, you can see it's sort of wobbly, and that makes it a bit harder for me. But I'm going to try anyway. I'm going to say that my release direction is that surface, and then I have this nice little tool that highlights the colors. Let's see. Just disable that. And then it's going to, the green surface now is anything that's above 2 degrees draft angle, right? As I go down here, you can see that now it's 1 degree. And this tells me that like this is not really manufacturable because it's too steep, so I need to fix that, right? as is this. So let's just leave that in here, the analysis, and let's try and fix this surface, which looks horrible. So the tool I'll use is called draft, and then I will say my pull direction is that, and then I will pull on that face like that. Since this is a very odd geometry, I'm not sure if this is going to be a success, but let's try it. Oh, look at that. Now it's green, right? So what I can just zoom in and see what I did. I just like angled all the faces slightly like that so they would release, right? So this is before. Look at this corner down here, and this is after. Right? So that's how you add draft to your models. Right? And you can do that for gussets, you can do it for anything. This is more of a problem, the thing that's going on the side here. This is actually quite problematic. I'm not quite sure how we would solve that. Maybe I would extrude this again, like part of it down, and then do something to it. It's not ideal that it's shaped like that. Yeah?
Why is it only happening on one of the sides?
Because it's not symmetrical, because I played with the shape and I did a lot of funny things with it.
Yeah.
Yeah. But the essence is draft analysis. The draft analysis in Fusion is not that good in that it's quite easy to see the green, but on the opposite side it turns blue, and blue is green only going the other way. And it's really hard to sort of figure out, okay, is it blue, is it something else, what's going on, it's so dark. So typically what I do when I do draft analysis is I do one for each direction, right? You can also use this tolerance zone. It's a bit complicated as well. So the tolerance zone is going to highlight whatever is sort of borderline acceptable. And then that means that if now this turned yellow, that means that it is, let's see, how is that? Yeah, it's more than 1 degree, but it's less than 1.5 degree. You need to summarize these two. Yeah, that's how you do it. The tolerance zone tells you like borderline cases. Don't worry about that here. Just disable it and use this. That's fine. And then this is sort of your draft on the opposite side, which should be -1. But I think that interface is super hard to read, like when I do this. So I'd rather do one draft analysis for either side. So I'll just do a new one, inspect, draft analysis, and then I will select that body, and then this direction, and then I will just swap these two. I think that works. No, it doesn't. I need to do that direction, like that. And that gives me like 2 draft analysis, one for the outside and one for the inside. Inside like that, outside like that. Yeah.
But on this side, the outside doesn't matter as much, right? Because it's like
The cavity?
shell. Yeah, the cavity.
Yeah, but you still need to release it, right? Like I need to be able, even though like for the Legos, that's really an exception. So normally you would like to have the same draft on the inside and that side. Actually, I might argue that it might matter more, because on the outside, maybe I want some texture, and that's going to be like the good-looking side, right? So I need to make sure that it comes out of the mold without being scratched. But it's like for the case of the Lego, it's actually quite a special case. What they do there is that they have a big draft on the inside. I'm not exactly sure how they do it, to be honest. They do some tricks, but I think the polishing helps them. And also the draft is not just to not rub against the mold, but it's also to let air into the mold, so it sort of doesn't like suck onto the tool. Yeah. Okay, so that was draft analysis and drafts and a lot of information about how to make injection molded stuff. But I think that the key takeaway here is to look at the parts from the headphones we took apart and try and learn as much as possible by how they are designed. Yeah. Any more questions? Okay, we're on time. Perfect. Should we do another break? Should we do till 10 past, and then we can do projects for the last hour? Is that okay?